So up to this point in talking about electrostatic potential energy, we focused on a single point charge. So we have some single point charge here plus little q, and there's some other charge elsewhere, which might be over here. We have a bunch of charges that generate an electric field. And the question we've asked is, what's the potential energy of this object as I move it around in space, given a fixed bunch of capital Q's. Okay, so we want to ask a different question now, and that question is, how much energy does it take to build an object like this? In other words, if I take point charges that are all starting at infinity and I bring them in one by one to build this object, how much energy would that take? Posed in a different way, if these charges weren't glued down, in other words, I had this bag of charges here and I released them, what would they do? How much would they fly away from each other, and how much energy would be released by that process? So if I have, for instance, a sphere that's positive charge throughout, right, like the exam problems that you had, if I were to release that positive charge, it wants to get away from each other, so it's going to run away off to, in all directions. How much energy will be released into the kinetic energy of those charges when I do that? Okay, so that's the other way to ask it. Now this is relevant because we're going to start talking about storage of electrostatic energy using devices like capacitors. And there what you do is you pack charge onto plates with the idea that you're storing energy that you can use at some point later, for example, in your iPod to make Angry Birds play or whatever. Okay, you're going to store some energy, release it, play your video game. There you go. All right, so let's look at this problem of assembling charge. Let's take a simple example, which is only 3 charges. Well, let's ask the question, if I have a charge distribution that looks like this, where I have 3 charges that are, put in a triangle. This is R12, this is R23, this is R13, the distance between them. The question is, how much energy does it take to assemble this, to put this together? So what I mean again is I take the charges Q1, Q2, Q3, they're all off at infinity, they don't see each other, there's no interaction, and then I bring them in one by one. Okay? So you imagine a sequence of steps where the first step is you place Q1, okay, Q1, okay, and then you place Q2, and then you place Q3, okay? All right, now when I place Q1 in that scenario, I start with nothing else around, and so I don't have to expend any energy. So let me go to the next page here. So I'll place Q1. There's nothing else around. The energy it takes to place that charge is 0. Okay, I didn't have to do any work against electric fields. Okay, so this is step 1. Step 1. Now step 2, now I have Q1 sitting here, and I'm going to place Q2. Okay, and the way we think about this is Q1 is going to be glued down. So as we do this assembly, if we have an object that's an assembly of charge, we imagine that we bring one in, we glue it down, we bring the second one in, we glue it down, and the third one in, and we glue it down. Okay, so Q1 is producing an electric field that Q2 feels as we bring it in, and we know that the potential energy change of Q2 due to Q1, if I move it from infinity to this location, is given by the charge Q2 times the potential generated by charge 1 at that location. Okay, and I left off the delta here because at infinity the potential energy we're defining to be 0. And so this second bit of energy I have to expend to place Q2 then is going to be Q2 Q1 over 4 pi epsilon naught R12. Okay? All right, and so now we've placed 2 of the 3 charges. Now let's place the third, so charge 3. So now we're going to have 3 charges, and as we place the third, it will experience electric fields. Did it again? There we go. It will experience electric fields due to 1 and 2 as we place it. So these distances again are R13, this is R12, and this is R23. Okay, so I'm going to expend energy U3 to place charge Q3, which will be Q3 times the potential generated by 1 at the location of 3. I probably should write it that way. Okay, so if I go back up here, I might write this as V12 up here. Okay, and plus Q3 times the potential created by 2 at position 3. Okay, so these two terms account for the work I have to do against the electric field of charge 1 and the electric field of charge 2 as I move charge 3 in. Okay, so this will be Q3 Q1 over 4 pi epsilon naught R13, and then I'll have Q3 Q2. Oops, Q2 over 4 pi epsilon naught R1 or R23. Okay, now I'm done. I've assembled the charge, so we can add up now the total energy that I spent to do this, and that energy is just going to be Q1, oops, I'm using lowercase, Q1, Q2 over 4 pi epsilon naught R12. That's the energy I spent placing charge 2 with charge 1 already there. And then I have Q3, Q1 for 4 pi epsilon naught R13, and then plus Q3, Q2 over 4 pi epsilon naught R13. Oops, R23. Okay. Now I can generalize this. So if I imagine more than 3 charges, you see the procedure. What I can show is that for more than 3 charges, I can write the following: that I sum over 2 indices, over I, and then over J. Okay, and the requirement is that I is always less than J. So here we have I less than J as a requirement. And then I'm going to have Qi, Qj, Qj over 4 pi epsilon naught Rij. Okay, so these two, this is the generalization of the above expression. And the reason I count I less than J is that this formally mathematically lets me write down this procedure where I'm placing one charge at a time. Okay, and every charge that I bring in, the next one will have to interact with more charges as I bring it in. Okay, and that's how you would assemble this charge distribution, is that procedure. Okay, now this is a bit of an unwieldy expression to deal with because you have this I less than J. The easiest way to do this is to use the following procedure. So if I imagine I have my distribution of charges, a bunch of charges here, and instead of imagining that I'm assembling the charge, what I would instead do is just imagine that each charge that I place is like the last charge. So I'm going to calculate an energy associated with each charge as if all the other charges were already there. Okay, so that's clearly going to overcount the energy if I sum all that up. But I can write that expression down. The energy to place each charge in the presence of all the others would be a sum over I and J of the same object. So now for each charge, let me start over again here. Okay, for each charge I, so what I do is I multiply Qi times the potential generated by everything else. And the potential generated by everything else is sum over J, where J is not equal to I, because I'm summing everything else. Qj, this is I, and that's J, 4 pi epsilon naught Rij. Okay. Now again, this is going to overcount, but it turns out it overcounts by exactly a factor of 2, and hopefully you can squint at that for a while and think about it and see if you agree. Okay, but these two expressions, this one and the one above, are identical, but this one's a little bit easier to deal with mathematically, so we'll use that one. Okay. Now I can write this another way, which is the way I argued it actually, which is that I can write it as U total. It's the sum. I need my 1/2. Sorry. 1/2 sum over I Qi times the potential due to everything else. Okay, and what I'll do is I'll just write that as VI. So when I say VI, I mean the potential that charge I feels due to everything else in the system. Okay. Okay, and so this is now our expression for the energy required to assemble a bunch of point charges together. I'll stop here, and in the next video talk about generalizing this to non-point charges, to continuous charge distributions.